Okay, welcome everybody. I'd like to welcome Bryce Bolin. There we go. Who's applied to join us and from Goddard to postdoc. And Bryce, if you could give us a little bit about your background, and then we're looking forward to your talk.
Sure. Thank you so much for having me here. It's great to be here. I'm looking forward to this discussion, talking about some topics that I think are a lot of fun. A little bit about my background. My name is Bryce Bolin. I am presently a NASA postdoctoral program fellow at NASA Goddard Space Flight Center. I am working with Keith Noll on studying asteroids and comets. Prior to that, I was at Caltech as a postdoc working with the Zwicky Transient Facility project as their solar system helper, as you will. Before that, I was at the University of Washington, where I did kind of an interdoc between my postdoc at Caltech and my graduation from the University of Côte d'Azur. And there I was working on doing asteroid simulations, but I also got into doing actual asteroid observations. The first paper I wrote that was observational was while I was there was about the interstellar object Oumuamua. That's kind of set me on a more observational path. But prior to that, I was at the University of Côte d'Azur, where I was studying the dynamics of asteroid families in the main belt, working under Marco Delvo and Alessandro Morbidelli. But that wasn't my start in astronomy. Where I really got started was at the University of Hawaii. It was kind of before my doctoral studies. I was a research assistant at the University of Hawaii Institute for Astronomy, working on the Pan-STARRS survey. And I think I see Ben Yang in the audience. I overlapped with Ben Yang a little bit there, and I remember we did a Subaru run together. So that was really an awesome experience getting to kind of shadow Mauna Kea observations. But primarily I was focused on asteroids. So I'm going to talk today about asteroids and comets. I've been studying these things for a while, so I love talking about them. So I hope you enjoy hearing about them as much as I enjoy talking about them. So should I go ahead and get started?
Yeah, please do.
Okay, I'm gonna, just for stability, because I have some movies, I'm gonna turn off my video. So that might help with bandwidth issues as I transition between slides to make things a little bit more smooth. But yes, I'm going to talk about, sounds very kind of clickbaity, buzzwordy, but it is for certain appropriate here, for real here, talking about AI uses and identifying asteroids and comets and wide field survey data. This is going to be talking about work that I did while at Caltech at working with the Zwicky Transit Facility at Palomar Observatory. So my opening slide here, I have a picture of an asteroid orbit called Ayló'chaxnim, which is a interior Venus object. And on the right panel here, I have a comet, C2022 E3, which was a comet that came pretty close to the Earth in February of 2023. So I'm just going to talk a little bit about the background. I know you already know this, but I talk about the orbital elements a lot here. Let's say major axis, eccentricity, inclination, perihelion, aphelion. I'm going to go into definition of different classes of objects where they're differentiated by these orbital element values. But this is just a standard slide here for definition. I'm sure all of y'all know these things very well, so I'm not going to dwell too much on this slide. But first, I'm going to talk about what are near-Earth asteroids, what are near-Earth objects. This is a kind of a movie of from the Minor Planet Center of the current known ensemble of asteroids within the orbit of Jupiter. As of today, we know that there's about 1 million asteroids in the Minor Planet Center's catalogs. The vast majority of those are in this green cloud here, which is located between the orbit of Mars and Jupiter, which is what we call the main belt. There's over 800. There's over a little over 800, 900,000 of those objects, all larger than a few hundred meters to almost the size of a small country. In the case of Ceres, about 1,000 kilometers in diameter. So you go from kind of dwarf planet-sized objects all the way down to about sub-kilometers from our current knowledge. But interior to this green ring here, we have this kind of reddish swarm of objects that cross the orbit of Mars. Mars is this red crossed circle that is in the just interior to the this green ring, and the Earth is the blue cross circle, and Venus is purple, if my eye color calibration is correct, and orange is Mercury. And so these are terrestrial planet crossing asteroids, which we know as the near Earth asteroids. In principle, the definition of a near Earth asteroid is one that comes within 0.3 astronomical units. This definition can be a little, let's say, flexible, because there are some objects which we do classify as near Earth objects, but by definition, they may not necessarily come within 0.3 AU, and I'll talk about that in a few slides. As of today, there's about 30,000 of these near Earth objects, which are known. Thousands of which are 1 kilometer in size, and it's predicted that there are about 1 million 50-meter size larger NEOs. So I'm going to talk a little bit about NEO origins. Where do they come from? We currently think that the vast majority of NEOs originate from the main belt. The Jupiter family comets can be a potential additional source of near-Earth objects. When I say near-Earth objects, I'm including both asteroids and comets. So just loosely, in terms of whether or not we know something as asteroidal or cometary, we refer to it as an object in the acronym NEO, near-Earth object. But in general, the vast majority of these NEOs come from the main asteroid belt, and they come this way by escaping through resonant escape hatches. And I have a little movie I borrowed from Bill Bodke that illustrates this. Bill Bodke shared this movie and gave me permission to use it in my presentation. And it shows the, sorry if I don't have that quote here on, I don't cite his name on the slide, but this is his movie he made showing the evolution of asteroids out of the Coronis family. So I'd like to point some things out on this plot here. On the x-axis is the semi-major axis. These particles on the y-axis is their eccentricity. So the particles that are being, let's say, simulated numerically in this kind of movie are red, but you might also notice that there are these green lines. 1J says 5 to 2, J 12 to 5, and J 26 to 11. Those are all marking the locations of mean motion resonances. That is, places where an asteroid will have a integer proportion between its orbital period and the orbital period of Jupiter. And when asteroids are in the vicinity of these green lines, their eccentricity causes the location of these resonances causes their eccentricities to evolve. Now you're probably asking, okay, well, asteroids just kind of stick in the same orbit. We have secular perturbations and so on and so forth. But what really causes them to diffuse? Well, the answer to that question is the Yarkovsky effect. It's kind of a two-step process. First process is that the Yarkovsky effect modifies asteroids through major axes, either pushing them outwards if they are spinning prograde, causing their major axis to increase in value. Whereas if they're spinning retrograde, that is along their rotation axis, if the rotation axis is they're spinning retrograde on, causes them to shrink in semi-major axis, that is, go to lower values of semi-major axis. And as their semi-major axes increase or decrease, they can run into these green lines, the location of these resonances. So they may have started out nominally at an eccentricity of around 0.05, but the yellow lines here are showing the evolution in their orbital elements, where they're evolving in semi-major axis due to the Yarkovsky effect. But as you can see, they're jumping their values are jumping or increasing as they're crossing these green lines, locations of these mean motion resonances and eccentricity. And so as the eccentricity evolves, their perihelion decreases. So if you're at a semi-major axis of 2.8 and your eccentricity evolves to say values of half or even more, you will start to cross the orbit of the terrestrial planets, first Mars and then the Earth and so on. And so it's this kind of a tumbling effect, a domino effect, starting with first the Yarkovsky effect, then going in the vicinity of these resonances, pumping up your eccentricity, which shrinks your perihelion, which causes you to encounter the terrestrial planets. And then that scatters your orbit, drastically evolves your orbital elements when you have these scattering planetary encounters. And then you can go into the usual near-Earth object definitions, which I will discuss in a minute here. But first, before I discuss the NEO object, near-Earth object definitions, I'd like to discuss a little bit again this plot, going back to this figure here that shows the main belt. And I'm sorry if I didn't explain to it a bit earlier, but this main belt shows in the bottom panel semi-major axis versus eccentricity for the main belt asteroids, and on the top panel semi-major axis versus sign of inclination. And so what I show here is that we have these kind of clearances where they are classically known as the Kirkwood gaps. But what I want to show here is that these gaps are where the resonances are, and that the dominant source of the NEOs are coming from asteroids that drift into the new 6, which has this kind of squiggly line pattern in semi-major axis versus sign of inclination. As it's inclination dependent, so it starts out very low in sign on the inner edge of the inner main belt, and then gets larger and larger, and traverses all through the main belt. And that's why you see this kind of clearing here. That it's not just a vertical slice; it's actually kind of a squiggly line. All along that squiggly line is cleared out areas of due to the cleared of asteroid due to the instability caused by the new 6. And on the bottom panel, I want to show the Mars crossing line. So as your eccentricities are being pumped up, if you get to a large enough eccentricity value, you can start to cross the orbit of Mars, and that's when you start to scatter in your orbit, in which can lead you down this crucible of planetary encounters, which causes you to enter near-Earth object space. So within 0.3, coming from 0.3 astronomical units of the Earth. So as of now, there are 5 near-Earth object classes. These kind of have been discovered in piecemeal. One was discovered most recently a few years ago, but the classical, the first known one, are called the amors. These are defined as objects which have a perihelion of less than 1.3 astronomical units, but do not cross the orbit of the Earth. So they have a perihelion minimum of 1.01 astronomical units and a perihelion maximum of 1.3 astronomical units. And the very first one ever discovered was 433 Eros. And it was a joint discovery, co-discovered by a French guy, Auguste Charlois, and a German guy, C.G. Witt, at Nice Observatory for Charlois, and Berlin Urania Observatory by Witt. And I have here on this little picture of the bottom right-hand corner the actual telescope where 433 Eros was discovered. It's not too far from where I did my PhD. I did my PhD at Nice Observatory, and this is literally in our backyard. But even though this was the first near-Earth object discovered, the first so-called AMOR object discovered, the namesake of the AMOR class, the prototype, is 1221 AMOR. And it's kind of a complicated reasoning why it's not called Eros, but in general, NEO classes start with the letter A. So it may be due to some kind of, let's say, a special thing with that we want NEO classes, a tradition of traditionally starting with the letter A. The next NEO class are called the Apollos. These do cross the orbit of the Earth. That is, they can have perihelia that take that go within the aphelion of the Earth at 1.01 AU, but they have semi-major axis of greater than 1 AU. The first known example of this type is 1862 Apollo, discovered in at the Heidelberg Observatory. And the next one after that is Acton. These cross the orbit of the Earth, but have a semi-major axis, kind of converse of the Apollos, in that they cross the orbit of the Earth and have a semi-major axis of less than 1. The first known example was discovered at Palomar Observatory using the Palomar 18-inch Schmidt by Eleanor Ellen, and it was given the number name 2062 Acton. And this is lower right-hand corner here, shows Eleanor Ellen at the Palomar 18-inch Schmidt. So she's pretty special person in my opinion, and yeah, she found a bunch of asteroids, including this one. And I think there's also a Star Trek spacecraft named after her, but I'm not entirely certain. So the next couple of NEO classes are asteroids, which we call inner Earth objects. These are asteroids that are located entirely within the orbit of the Earth. And these are the most rare type. So the Amors, there's about 12,000, which are known. About 50% of the NEO population are Amors. Apollo's about 50,000. They're the most populous of the NEO classes. Attons, there's about 2,000. But these inner Earth objects, which we call Ateras and Ayló'chaxnim, or Aylos for short, there's only about 3 dozen of them known. And so I'll discuss these really quickly. So the first of these classes, inner Earth objects, are called Ateras. They also have a kind of an unofficial name, aphelion. So Atera is the Pami goddess of creation, which is associated with the morning star idea, which is classically, which we now know as Venus. But aphelion is the Hawaiian word for orbit. And this is kind of the split between the namesake and the first discovery, because I'm going to play a little bit here. I'll explain that in a second. But these objects have aphelia just within the perihelion distance of the Earth. So they have maximum orbital distance from the Sun, 0.983 AU. And the very first one discovered is 1998 DK36. This was discovered by Dave Tholen with the UH-80 in 1998. And unfortunately, it was a very small object. I think it was only about 50 meters in size. So it was seen once as it was passing just within the perihelion distance of the Earth with the survey that Dave Tholen was doing with UH-80, and never recovered again. So it has never been seen again, and will not receive a numbered designation. But it is technically the very first of these inner Earth objects discovered. The namesake of this class is Atera, because it is the first of this class to be numbered and named, and it was discovered at the Lincoln Labs NEO search that was running in the early 2000s.
Hey, Bryce, excuse me, does it have a satellite?
Yes. So in the upper right-hand corner, I have the Doppler delay image taken by Arecibo Observatory of Atera. And these data were taken on 20 of January 2017. And the funny thing is, I actually helped with those observations. I was visiting Arecibo Observatory for about a week, and they had this object on their to-do list, and I sat in and helped them with shadow is a better word, but I was observing with them when they took these data, and they discovered 2, I would say, notable things, pretty special about Atera. One, it has a satellite, which you see here in this Doppler delay image, this little thing here. So it is a binary near-Earth asteroid. It is the only known binary inner-Earth asteroid. And the other remarkable thing about it is that from the Doppler delay images, we deduce a diameter of 6 kilometers. 6 kilometers. That is a monster of an asteroid in near-Earth objects, in the near-Earth object population. So I have a project. So I was just actually talking to a graduate student where we're studying Atera in detail. And we have there's a paper, I believe it's in review, about the radar data, and we're working on another paper about the actual observations that we've been doing to study this object. But we think there's something pretty interesting going on there, given that it's a massive 6-kilometer object. This next class of object, sorry about that, is called Ayló'chaxnim. And these have Qs within 0.718 AU, that is within the perihelion distance of Venus. So these are inner Venus asteroids. So they are kind of on the borderline of what you might call NEOs or not, because by definition, NEOs come within 0.3 AU from the Earth. So they pass just within interior that could be inside the Earth by more than 0.3 AU. So it's kind of a gray area if they count as NEOs or not. But for the purpose of the infrastructure that is devoted to cataloging and NEO observations and studying them, they are NEOs. But not to brag or anything, I discovered this at the Palomar using the Palomar 48-inch in 2020, we got the over the course of years, we got a number of recovery observations of it that were sufficiently of sufficient quality to precisely determine the orbit enough to get a number designation from the Minor Planet Center, which the IAU allowed us to submit a name. We actually consulted with the Palma band of the San Luisino people who are the original inhabitants of Palomar. And when we asked them to name the object, they agreed. And they came up with this name, Ayló'chaxnim. It was originally Ayló'chaxnim, which means daughter of Venus, but that was too long, too many characters long for the Minor Planet Center to name an object. So they came up with a shortened version of that name, Ayló'chaxnim, which is a similar meaning, girl of Venus. So we found it was to be fulfilling a criteria that NEO classes should start with the letter A, and B, be something semi mythological, because all the other NEO classes are named after, I don't want to be a nerd here, but Amor is the Roman god of love. Apollo is the Roman god or Greek god of music and the moon, I think. Aten is the Egyptian god of the sun. Atira is the Pami goddess of creation. And so what more appropriate name to name a inner Venus asteroid is daughter of Venus, which is a mythological figure in multiple ways. So I'm going to talk a little bit about how Ayló was discovered. The person, so Dave Tholen was really kind of the one in the CCD era, at least, who pioneered the search for asteroids interior to the orbit of the Earth. He thought of looking for Trojan objects, which are objects that are cohabit the orbit of the Earth. And in doing so, he also covered part of space, part of the sky, where asteroids interior to the orbit of the Earth are found. But the person who really kind of quantified where interior actually describes interior Earth and interior Venus objects in detail was Giancula Massi. He didn't call Atiras and Aylós weren't discovered then, so he called them inner Venus asteroids or inner Earth asteroids. But in 2003, we had the near Earth asteroid model, which in the population included a number of objects, number of inner Earth and inner Venus objects. So he simulated the location of those objects in the night sky, and he found that the majority of these objects are found very close to the sun. So this is a plot showing the ecliptic longitude with respect to the sun, and the x-axis in ecliptic latitude with respect to the sun on the y-axis. And it's a heat map. So the more red the color is, the higher the sky plane density where these objects are found. And so the vast majority of these objects had the highest, where they are found, had the highest sky plane density of these objects is within 50 degrees ecliptic longitude with respect to the sun, and about plus or minus 10 degrees ecliptic latitude. So he describes in this paper that if you want to find these things, you have to look pretty close to the sun. And that's a very unique observational challenge, which I'll describe in a little bit of detail here. So how does one actually, how does one actually go about finding a Tiras and Aylós? And this is kind of a basic geometry of the problem. What that entails is that when you have exterior objects, they can have angles between that and the sun as viewed from the Earth. We call solar elongation between 0 and 180 degrees. So, obviously, if you're around 0, that's solar conjunction. You don't want to look for asteroids then. So you usually wait to when they have a sizable solar elongation of at least greater than 90 or more degrees, which makes them oppose opposite direction from the sun and much easier to observe in the night sky. But for inner Earth objects, the maximum distance that they can have as viewed from the Earth due to their orbit is requires that they have a much smaller solar elongation angle. For interior Earth objects, it can be at most 90 degrees if they're right next to the Earth. But for most interior Earth objects, they have smaller aphelia. They'll have smaller heliocentric distances, which means that they have smaller solar elongation angles. And for the Aylós, for intravenous asteroids, it's even worse because you're confined within the orbit of Venus. The maximum angle you can have is about 47 degrees. So how does one find asteroids within 47 degrees of the sun? It's pretty difficult. It's not usual nighttime observing. But just to give you an idea, that's kind of the maximum, the theoretical maximum that Aylós can have. In reality, there's orbital distribution, probability distribution of the aphelion values for Aylós as determined as described in the INEO model. And the theoretical maximum is 72 AU, but on average, the actual maximum solar elongation that most Aylós can have is going to be smaller than that. You're talking right around 42 degrees or less on average. So you have to look pretty darn close to the sun, which makes hunting for these things kind of a challenge. So Ayló'chaxnim, the first intravenous asteroid, was discovered on the 4th of January, 2020, in the evening sky. So this is a little solarium magic here, showing the view south of west from Palomar Observatory at the start of nautical twilight. So nautical twilight is defined as the time in which the sun is 12 degrees below the horizon. And so it's around 7 p.m. Pacific time on 2020 January the 4th. So you can see there's Venus there. You can see Fomalhaut. We can see Altair. Above the horizon. This isn't actually what Palomar Observatory looks like. It's kind of a dummy surrounding, but this is where the Palomar 40-inch what you would see with respect to the horizon is viewed from the Palomar 48-inch this time in night. And I've drawn here in red line the ecliptic, and this is Venus. We can see Venus there. That kind of gives you an idea of where things could be inside the orbit of Venus with respect to Venus. And the ground is this green line, and the plus 20 degrees altitude is this orange line. Now, plus 20 degrees altitude is significant here because that is the minimum altitude that the Palomar 40-inch Schmidt telescope can point. So, we're already having to look pretty close to the sun, but we also have constraints on how close we can look to the ground. Not many telescopes can look exactly at the horizon. Most have to look at some angular distance above the horizon. And in the Palomar 40-inch case, it's 20 degrees. So we're going to remove the ground here, make the ground disappear so that we can just look at where the sun is. So this is the sun about 12 degrees below the horizon at the start of nautical twilight on January the 4th, 2020. So this is the location of the sun here in this purple square. This is about the 12 degrees latitude distance, noting its angular distance below the horizon. I would just like to note here is that the duration of twilight, that is the duration of time between nautical twilight and astronomical twilight, is not consistent through the year. That is the amount of time that is between when the sun is between minus 12 degrees below the horizon and minus 18 degrees below the horizon. can vary as a function of time throughout the year. So I've shown here on the x-axis day of year, on the y-axis duration, and this blue line is showing the duration of astronomical twilight. And during this
Bryce, you cut off. Can't hear you.
winter, it's a bit shorter. You also know that it's anti-correlated with the percentage time of the duration of night. In this case, I'm plotting it here in orange, 5%, 5.5% of the total nighttime plus the duration of astronomical twilight. And so there's actually there's this kind of anti-correlation, is that you have less time in the night, but even though twilight lasts longer, you have less time in the night to actually observe total time between astronomical twilight and evening and astronomical twilight. And so in the summer, this is about, from Palomar, a latitude of 33 degrees, this is about 40 minutes, 40 minutes of total time, but can be as short as about just under 30 minutes during winter. And so this is kind of, this discussion of latitude is important, because as you go to higher latitudes, twilight can last basically all night during the summer solstice. So it's the latitude of Paris at 49 degrees. Twilight can last for about an hour. The most strict definition of twilight, we're talking about things like civil twilight can last for several hours. So when I say 1 hour duration, that we're talking about nautical to astronomical twilight. But if you go even a bit higher, like I think it was Herschel, the British astronomer, he couldn't do any observations at all during the summer, because in Britain, you're at even higher latitude than Paris, and you basically have civil twilight lasting all night long. So he had to wait until August, September before he could actually do any observations. And so he would have parties celebrating the return of the time, the year where you could actually do observations, where civil twilight wasn't lasting all night long. But the upside here is that you get a lot of inspiration for really cool sunset paintings. Sunset lasts so long, so it gave Claude Monet, this is a Monet painting here, he had given him lots of ample time to do his impressionist paintings of various sunsets around the locations of Paris. So we can thank that for the helping beautiful art that he made. But going back to science here from art, shifting gears back to the science, I show here the kind of the layout in the sky, where one can actually do a survey for objects in the twilight sky. So you have this limit of 20 degrees altitude, and it's this orange portion. And you also want to kind of hug the ecliptic. So really, the kind of area of sky where you can actually do a twilight survey is in this kind of rhomboidal blue shaded region here. That is plus or minus 10 degrees of the ecliptic, and getting as close as you can to the sun. So just how close can you get to the sun? It's about 40, using the Palomar 40-inch, we can get about 40 degrees from the sun, where we can start covering the sky at the start of nautical twilight. Now, we have a little bit of an advantage here. I'll discuss that in a minute, is that with Schmidt telescopes, so you have a pretty wide field of view. So that allows you to get a little bit closer to the sun than would normally be allowed by your pointing if you had a narrower field of view. Gives you a little bit extra leg room there with how close you can get to the sun. So I'm going to talk about that, segue into that, talking about the Zwicky Transient Facility camera. It has a angular area of 47 square degrees, so it's about 7 degrees on each side. And so along a diagonal, you're getting a sizable chunk closer to the sun. If you have that diagonal pointing directly towards the sun, you're getting 5 or more degrees, about 3 to 5 degrees closer to the sun than you would be allowed by just the 20-degree pointing limit if you had a much narrower field view. So in addition to its large field of view size that assists with the observations of objects in the twilight sky, it has a pretty decent limiting magnitude, about 20.5 in V during dark in quote dark conditions. In twilight conditions, it's going to be not as deep limiting magnitude, but during dark time at nominal air mass, we get a limiting magnitude about 20.5. I'll show a plot a little bit later what the actual limiting magnitude is. But in 30-second exposure, we take exposures in a 30-second cadence. We can get to 20.5 in about 1 to 2 arcseconds seen, pointing as low as 20 degrees, and having that little extra diagonal distance can allow us to get a bit closer to the sun than point a little bit lower than just 20 degrees elevation closer to the sun. So that's kind of the discovery aspect. We're using ZTF to discover objects. To recover things, I'm using something called the Global Relay of Observatories, Watching Transients Happen, acronym growth. Like, yeah, it's a mouthful. It's not the best acronym in the world, but basically, this is a worldwide network of observatories, 1 to 2 meter-ish size telescopes, to follow up transients detected by the Zwicky Transient Facility in order to help them to be discovered. And so I've had there's telescopes through in San Diego. We have telescopes in Taiwan helping us out, as well as telescopes in Europe. In India, helping me with the use of this the Growth India telescope to follow up these objects, as well as in Taiwan using the Lulin 1 meter telescope, and as well as the 1 meter at Mount Laguna Observatory near San Diego. So thanks a lot to these individuals for helping me out recovery, assisting with the discovery effort of this survey. I have a little movie here showing a fast moving object. Just for fun, even though I'm not going to talk about fast moving objects here, but this is just one object that we discovered thanks to their help. So this is the pointing map of the Twilight survey, where on the night sky, with respect to the sun, we are pointing the Zwicky Transient Facility's giant field of view camera, accumulated between 2019 September and 22 September, so 3 years of observations, observing between -12 to -18 degrees twilight in the morning and the evening. And as you can see here, I've also overlaid the location of our discoveries, which I'm going to talk about a little bit here. But as you can see, the kind of where the majority of these pointings occurred, it's about 20 degrees ecliptic latitude, not exactly hugging the ecliptic. But due to 33 degrees geocentric latitude of the location of Palomar Observatory, this is kind of the closest that we could get to the ecliptic. So if we had an observatory closer to the equator, we'd be able to look closer to the lower ecliptic latitude. But it also does help us to observe higher inclination objects, which I'll discuss in a minute. So talking about the sun-centric distance, this is a plot showing the cumulative fraction of the sun-centric distance of the pointings of the area of sky covered by the Zwicky Transient Facility in the Twilight survey. And this black vertical line here shows the maximum angular distance from the sun that IVOs can have. And so roughly speaking, about half of the ZTF Twilight survey pointings are in this angular range. This is kind of the maximum amount of coverage that we can get given the amount of time that we have to cover the sky, while it's still observable given the 20 degrees elevation pointing limit of the Schmidt telescope. I also overplotted the angular distance of various objects that we've found. We found an object that was about 32 degrees from the sun. That was about the maximum as close we can get. We can detect objects as close as 35 degrees from the sun. And indeed, I've plotted here in orange so the angular distance to the location of Ayló, and when it was discovered and recovered, and it's about 40 degrees from the sun. So in terms of limiting magnitude here, this is the limiting magnitude of the survey. About half of the pointings have a limiting magnitude of about 19.5. This is a 5 sigma detection limit in R band. Now there is a correlation between the angular distance from the, or say anti-correlation between the sensitivity and the angular distance from the sun. But this is the average of all pointings. This is showing the performance as a function of sun-centric distance and limiting magnitude. And as you can see, as we get closer to the sun, as the sun-centric distance decreases, as you go within, particularly when you start going within 40 degrees, 45 degrees, the performance drops quite considerably. So this is a kind of a heat map showing the number of visits and the limiting magnitude of those visits as a function of sun-centric distance. And I plotted in green this kind of a running mean. And as you can see that the mean we have a peak sensitivity around just a little over 20.5 for angular distances greater than 55 degrees, but that drops considerably as you go to smaller sun-centric distances, where it can be as low as 19 for fields that are as close as 40 degrees from the sun. And this is kind of where we found Ayló. Ayló was discovered at a magnitude of 18, which I'll discuss here. So these are the discovery images of Ayló on January the 4th, 2020. Detected in 4 30-second R band images with a measured magnitude of 18. The limiting magnitude of the images is about 19. It was given a provisional designation of 2020 AB2. But this is also kind of showing the location of where it was in the night sky when it was discovered on January 4th, kind of just barely outside of our 20-degree altitude limit. But I mentioned, in addition to discovery, we do recovery, thanks to the efforts of individuals at Caltech, as well as some helpers at SOAR and Magellan. We were able to recover this object in 2020 November, 2021 July, and the combination of the discovery arc and the arc going all the way to 2020 July allowed the object to get numbered, receive its number designation, and thus be named, and thus be the prototype of the inner Venus class of asteroid, which will forever be known as Aylós. You have Atiras, Apollos, Saturns, and so on. And so now we have the Ayló class of objects. This is the orbit. So it has an aphelion of 0.65 AU. So well within the orbit of Venus. It's technically not an NEO because it has a minimum Earth distance of more than 0.3 AU. So technically it's not an NEO, but come on, it's an NEO. Like, it's in the NEO class of objects. It has the smallest aphelion of all known asteroids. And I think the second it's the third smallest semi-major axis of all known asteroids, with an A of 0.55 AU and an orbital period of 151 days. In addition to, while in the course of this survey, we found several other inner Earth Atira objects. We found 4 Atiras. At the time this survey was occurring, there was only about 24 known Atiras. So we discovered, roughly speaking, 1/5 of all known of these type of objects, and 100% of all known Aylós. No one has found another Ayló yet, so we should keep on looking for these things. They're pretty interesting. So in addition to searching for the object, I've done a preliminary analysis on the survey completeness estimates of the coverage of the population of Aylós. So using the NEO model, I've simulated the detectability of Aylós, because there's a population of Aylós in the NEO model. And these plots are showing an orbital element space, semi-major axis in the top left-hand panel, eccentricity in the top right-hand panel, inclination in the bottom left-hand panel, and absolute magnitude in the bottom right-hand panel, what the quote completeness is as a function of orbital elements. So the gray histograms and all four of these plots correspond to the left-hand y-axis number of synthetic objects. And it's basically resampling the NEO model by a factor of 1,000, because the NEO model predicts a very, very low number of Aylós. So in order to get good statistics for our population, we oversample it by a factor of 1,000. So that's why you see number of synthetic objects in the hundreds there. And on the right-hand y-axis, we have the completeness, the fraction of the population covered. It's not the number of objects. I'll get to the number of objects that we would expect to detect, but it's like sort of the fractional coverage this is a preliminary estimate of the Twilight survey. And so for Ayló, there we find a 2 sigma discrepancy between the discovery of Ayló and the predictions of the NEO model. Now, I think, in my opinion, I have evidence that supports that the discrepancy could actually be much larger, because what dominates there's of course systematic inherent systematic uncertainties, and when you do these kind of simulations. But one of the main things that dominates the estimate is the uncertainty on the object size, on the object's absolute magnitude. And for various reasons, that's pretty hard to do for inner Earth objects, because they have a very narrow range of phase angles, which they can be observed at. But this object has a size of about 2 kilometers or larger, and we think that given its size, that we would only have a 5% chance of detecting it with our survey. So now I'm going to get into a little bit more speculative. This is kind of on my future work plans. But I mentioned in a few slides ago, that the majority of near-Earth asteroids originate from the main belt. But if we are seeing a discrepancy that would explain the occurrence of Ayló, it may imply that there has to be an additional amount of these objects in the NEO population, more than can be described by just assuming that NEOs originate from the main belt. So this would suggest an additional source of asteroids in the inner solar system. And so, you can chuckle, I mean, we'll see how this goes in the future with future observations, and I'll discuss future prospects for that. But a future source of a potential additional source of asteroids, which might explain this discrepancy, could be inner Mercurian belt of objects. So there are stable regions inside the orbit of Mercury between 0.1 and 0.2 AU. Yeah, I know, it's funny, right? It's not the best plot in the world, but there is actual dynamical evidence that you could have asteroids remain inside the orbit of Mercury on billion-year timescale. Because that's always been kind of a mystery, is why does it seem like as though Mercury is the closest in thing that could form in the solar system, when we see evidence of much closer in things forming in exoplanetary systems? We've seen evidence of massive amounts of dust originating from well within the orbit of Mercury around other stars. The Parker Solar Probe is detecting increasing flux of dust particle counts inside the orbit of Mercury as it's going in these really small perihelion dives into the sun. You also see craters on the orbit of Mercury that seems like they may have originated from impactors coming from inside the orbit of Mercury. And so, it seems that this isn't just a goofy speculation, that the discovery of Ayló and its this apparent discrepancy with the NEO model, which I think I have evidence of. I'm not going to present today, but I have evidence that the discrepancy could actually be quite larger. That it could be the first, let's say, direct and indirect evidence that there is an inner Mercurian belt. And I don't want to get too power trippy here or whatever, on a soapbox, but one can draw an analogy with the discovery of the Kuiper belt. The discovery of the Kuiper belt was predicted, let's say, I don't want to get to the too further back history, but I'm going to talk a little bit about the results of Julio Fernandez. He found that there was a discrepancy in the observed fluxes of comets coming from the ecliptic. in the Jupiter family comet population. He found that there was a larger number of objects than could be explained by a isotropic source surrounding the sun, coming from the ecliptic, that could only be explained, or could be preferably explained, by a source of objects coming from within the ecliptic, a reservoir of comets exterior to the orbit of Neptune, which was, of course, the Kuiper Belt. So it could be that, yes, maybe it's impossible to stare directly at the sun and find asteroids inside the orbit of Mercury. I mean, you have angular scales, angular distances of within 10 degrees or less. You have to look inside 10 degrees of the sun. Maybe that's impossible to do from the sun, from the Earth. Could be difficult to do from space too, but maybe the way to ascertain the existence of an a putative intermercurian belt, is by observing the downstream products of these objects as they diffuse out of this intermercurian belt, just as like the Kuiper Belt diffused out members as the end members were the Jupiter family comets. So we'll see. I mean, this was compelling enough reasoning. Yeah, I don't want to take all the credit here because it'd be kind of, megalomania out there. But Rubin Observatory is going to do a Twilight survey. This is from Jones et al. 2023. She simulated the solar elongation. She simulated the performance of the survey, the sky coverage of the survey, that is actually going to include in this baseline a Twilight survey modeled after the ZTF Twilight survey, and it will be able to cover portions of the night sky well within 40 degrees. So I'm showing here, this is solar elongation versus number of observations for the Rubin Observatory survey. The blue is kind of the baseline simulation, what the normal cadence is. But there is actually going to be allocation, some portion of morning twilight time to look for objects inside the orbit of Venus. And that's this orange portion of the histogram that can go as close as 35 degrees from the sun. So there could be potential for additional discoveries in the near future with additional Twilight surveys. It's predicted that the Rubin Observatory Twilight survey will find half of all Ayló's 100, 200 meters or larger. So if they're out there in numbers, they will be found, and then we can do the work, the calculations of determining whether or not there is truly a discrepancy between what we observe and what we think this really accounts for the population of near-Earth asteroids. So I'm going to talk a little bit about comets here. I've droned on quite along, but I'm going to talk about comet observations and comet discoveries with ZTF. This is kind of a classical problem with all sky surveys, is that it's actually pretty hard to identify extended objects, because in short, they are often confused for detector artifacts. You have light leakages, you have various elements of the optical path that results in there being diffuse looking sources on the image plane. And processing pipelines are tuned to basically reject these sources. But the sad consequence of that is that while they are taking into account for all these diffuse detector artifacts and rejecting them in order to limit the false positive rate, they're also throwing out a lot of true, real extended sources, i.e. the comets. Extended transients are victims of this culling, cleaning of from the data stream, from the various extended comet looking like artifacts. It unfortunately results in the rejection of real comet detections. And so this is a picture here from ZTF of 2I Borisov, the second interstellar comet as observed on May 2019. If y'all are fans of interstellar comets, you know that Borisov was discovered in the fall of 2019. And so this is a precovery image. And so this is a pretty low signal to noise detection. But if ZTF had not been rejecting all extending sources, including comets, very well could have discovered Borisov months before Borisov discovered Borisov. So a possible solution to this is to come up with a way to circumvent this cleaning process. So the solution I took here was to use deep learning to identify comets on a per image basis. So in short, to describe what deep learning is basically you are training something like an AI system, a neural network, to identify objects on a per image basis. So this is using something called a convolutional neural network. Neural networks are pretty good at finding trends in data that they are trained on to find. And a convolutional neural network is a way to do that efficiently for images. You basically are sweeping over an image with a kernel that is fine-tuned to examine a certain subset of pixels in a given time, looking for the features that would represent a comet-like object as trained on based on a set of actual training data. So this is an example of some comets that were used to train a deep learning neural network to identify comets. There's of course very famous 29P Ayló'chaxnim in the upper right hand corner there. And on the bottom left hand corner, we have C2019 D1 Bolin, discovered by Heather Bolin, given this name. And this provides kind of like a catalog of comets at various different scales and morphologies that allow us to kind of cover the full phase space extent of which we would expect comets to look like and be identifiable by a machine learning network. So I'm not going to go into too much detail about how the Tails network architecture works, but when you are feeding data in there into a neural network, there's various hidden layers. It comes in various layers. So we have a way of looking at the last few layers of these neural networks and efficiently combining them and compressing the outputs of these feature maps into a variety of different subnetworks, which then eventually results in the computation of a set of values, P sub C, X, and Y on the right-hand side. That is the probability of an object being a comet in its X and Y position. So I see there's some people, some chat going on here. Okay. Oh, thank you. Basically, using this network, what you input into it are the science images, reference images, and the difference between the two. And output comes a list of candidates, let's say selected objects that the neural network thinks could be comets with 3 different values. The probability that candidate could be a comet as well as X and Y position on those images. So it doesn't actually use any linking algorithms or any kind of moving object pipeline. It's looking purely at the pixels of the images themselves and detecting comets on a per image basis, on a single image basis. And so this is kind of the false positive and false negative rate for the p-score threshold, is that for 50% or larger, we get a false negative rate of 1.6% or smaller. So that's pretty decent in terms of not producing a lot of false positives. So we tested this out. Our train network on finding known comets. So we tested out, of course, I mentioned Borisov before, and as well as C2010 U3 Bottini. But we actually made a discovery of a comet. This is the first AI-assisted discovery of a comet, C2020 T2 Palomar, which is very fitting because, there's this movie in the 80s called Terminator, and early 90s Terminator 2. So for something where the machines are taking over and replacing the jobs of astronomers with AI, I think the name T2 for a comet is very appropriate for a machine-driven, AI-driven apocalypse in a certain respect. I'm totally kidding, of course, but we use this network on just a very small set of the Twilight survey data. So far, it's only used on just a small set of the CTF data, but 5 to 10% over the course of several years. And in that time period, we discovered about 10 comets, which doesn't sound like much, but when you're running on just a few percentage of the data, if you were to say run on 100% of the data, this would be 80 comets, which isn't bad for a B limiting magnitude 20-ish survey to be doing, especially in Twilight survey where living magnitude is even worse. It's more like around 19 and a half. You might notice here that most of these are long period comets, but you might notice one here. Well, this is kind of like a spaghetti diagram of all the comets smushed together in one plot. But yeah, you can see the majority are parabolic comets. There's a few short period comets. It's pretty difficult to discover short period comets nowadays because most of them have already been discovered, especially for such a bright living magnitude survey like ZTF. Usually what happens is they get attributed to some previous discovery. They get linked to a previous discovery, but the majority are long period parabolic comets, and a handful are periodic comets, Jupiter family comets. So there might be one from the list that you might recognize: C2022 E3, ZTF. It was discovered on the 2nd of March of 2022. I found it, I didn't really think of it as anything special. I was like, yeah, okay, sure, whatever, another comet, woohoo. But the world thought differently. It was or starting around the fall of 2022, it started getting phone calls from various people in the news saying, "Hey, well, this the comet C2022. It's getting pretty close to the Earth, and it got pretty bright around V of 5, and it was on the cover of Newsweek, Time Magazine, Sky and Telescope. It kind of got a little bit out of hand because it's a pretty ordinary comet. There's nothing particularly special about it except for the fact that came close enough to the Earth to be visible, almost naked eye visible. I drove out to to the desert outside Las Vegas and saw it with my naked eye. It was pretty cool. Discover a comet and then go outside and see it yourself. But yeah, you can scratch off your bucket list, I guess. But yeah, it got all over the news. I know people weren't too happy about that because it wasn't a very special comet in reality, but people love taking pictures of it. But here's the discovery images. This found in the Morning Twilight survey in March 2nd, 2022. This is a compilation of or a single image here of one of the discovery images, and then kind of a stack of the first and second, showing the relative motion between the first detection and the second and the last detection. This is the orbit. It came within 0.3 AU from the Earth in early February 2023. Reached V of 5, and it was visible from most of the northern hemisphere. So, like when I was working at Pan-STARRS, we found a number of quote unquote naked eye comets, but they were all, the viewing geometry was such that they had very large negative declinations. So only people in the southern hemisphere could see them when they came close to the Earth. But E3 had a declination of, I think, 22 degrees. So the majority of the Earth's population is in the northern hemisphere, gave them an opportunity, a potential large portion of people to be able to see this comet at a reasonable declination and solar elongation. Solar elongation, when it came this close, was about 120 degrees. So it's not like a super, early sun grazer comet or something like that, where you have to go outside and in the wee hours of the morning to see. This is actually something you could see in the middle of the night. And I did, I myself drove out to the desert a couple of times to look at it, and yeah, it was definitely a comet. Nothing like Hale-Bopp, but still kind of cool. We took a spectrum of it with Zwicky, sorry, not Zwicky Transient Facility, but with the spectral energy distribution machine. It's an IFU spectrograph, and we detect CN, C3, C2, maybe some forbidden oxygen, and got molecular production rates for CN, C3, and C2 of 10 to 25, 10 to 24, and 10 to 25. So seems like a pretty ordinary comet in terms of its gas to dust ratio. Imaging wise, this is a G-band image from the Palomar 200-inch. Kind of a little bit of overkill, but it's engineering time here. So these were taken in 1st of February when the comet was about 0.28 AU from the Earth. And in the G band, you cover some of those cometary gas features, and you can actually see the jets coming from the nucleus. So these are gas. The gas seems to be collimated into jet-like structures in the interior of the inner coma. So this is probably, in my opinion, the coolest picture taken of E3 by Javier Caldera. He is a Spanish astrophotographer. Took this picture here, which I think I'm using in my background, my Zoom background, and shows quite nicely the full extent of the coma. This is nearly when the Earth was crossing the orbital plane of this object, so you can see quite nicely the cometary features kind of edge on. You can see there's an ion tail as well as a dust tail, and it has a nice glowy green color. Then it was called the green comet. I know all comets are green, but that's what the media called it. There's also some nice pictures taken of the comet and Mars, and even inspired the Beaux-Arts. This is a astronomer at Griffith Observatory who is also artist and scientist all in one, and who drew their interpretation of the comet. So this is a summary of my contributions. I got some QR codes here pointing to the papers that I published about the work presented in this talk. So check them out, and let me know if you have any questions.
Great. Thank you very much, Bryce. Got a few people left. Any questions for Bryce?
Thanks, Bryce. Great talk. I have a question on the statistics on Ayla type objects. You talked about the completeness and the H magnitude plot. It seems to be sort of counterintuitive. If you can go back to that slide,
Sure.
I don't know how. Yeah, it's almost flat. I was a little surprised. Any particular reason?
Yeah, so that is due to the fact that in this area of phase space, going out to absolute magnitude of 18
Mhm.
is, so Aylo has an absolute magnitude of about 16.25. So in order to get good enough statistics, I was shooting for order of several thousand objects. So I only went out to about 3 sigma of the absolute magnitude. So it's 16.25 plus or minus 0.6. So I only integrated objects out to absolute magnitude 18. This also assumes a limiting magnitude of 20.5, because when I did this completeness calculation, we had very limited data.
Okay.
So I had to use two things. I had to use a limiting set of pointings. So we had just started the Twilight survey in September of 2019. So we only had several nights. We only had several months, and it wasn't like it was observing every night. Then we had a lot of bad weather. So the actual number of nights, usable nights, was actually only about 3 dozen. And half of those were in the evening. So that, in order to calculate estimate of completeness, I wanted to limit myself to objects which I knew definitively were well within the discovery, like 5 sigma or more of the limiting magnitude. And I also had to, due to the limited coverage at the time, I had to use main belt asteroids to estimate the completeness. Now, with 3 years of data, I now have an actual sizable amount of objects detected at similar solar elongations as the Ayló's and Asteroids. And I think I show here that indeed, where Ayló's are found inside this line, the limiting magnitude is a lot lower than 20.5. So when I did this initial preliminary estimate using the 20.5, it was well within basically everything within that range of 15 to 18 absolute magnitude was detectable. It was more of, let's say, whether purely geometric coverage, the proportion of CTF pointings that could cover that close enough to the night sky within a single given Twilight survey session on average. So I'm thinking that it's not good to be less faint, but with 3 years of data, I'll be able to do a much more detailed model of the detection efficiency.
Okay.
And and so I'm thinking, so one thing I show in this plot here, I know it's a different slide now, but I show in circles here. This is the actual magnitude the object was discovered, and it's kind of hard to see here. So I really jumbled on here. I apologize, but the pluses show the actual limiting magnitude. So for Ayló, the limiting magnitude that night was closer to 19, so it's only one magnitude fainter than the actual. And Ayló is an H of 16 object. So an H of 17 object would basically be on the border of detectability. So when I'm actually able to have enough of these data where I can have enough of these observations at these smaller solar elongations, we can actually get the completeness curve that is not only completeness versus the observed apparent magnitude, but completeness as a function of this additional parameter that is the sun-centric distance.
Okay, thank you.
Well,
I think that was a good question.
Thanks, Nolan. Well, hey, thanks much, Bryce. I guess we will go ahead and shut it down now. And thanks for your presentation, and we'll be in touch.
All right, thank you so much.